Last time we started section 3.4, and we were taking a look at concavity and the second derivative test. We were in the middle of example number 2, so looks like this is where we got to. Does that match up with y'all's notes?
Yeah,
We had a number line drawn. Do we draw this down here? Yeah. Okay, cool. All right, so what we need to do next is, or let me remind you where we were in this problem. Our goal is to find the points of inflection and then to discuss the concavity. We had gotten to the point where we took the second derivative and we found out where the second derivative was equal to 0. Those are potential points for inflection points, and they're places where, of course, then the concavity could change. So we want to test what happens for the concavity on those areas. And concavity is always determined by the second derivative. Okay, so we found where the second derivative is equal to 0. We created our number line, and we're going to test what happens in those intervals in between and before and after the locations where we might have potential places where the concavity changed. So we're going to take test points, and we've done this test point idea before. So can somebody give me a test point that you might choose before 2? 1 or 0, either way. Yeah, those would be good. Actually, let's do 0 just because it's a little bit friendlier. Nothing wrong with 1, but... How about a number between 2 and 4? 3 would be great, right? Well, it's not the only number, but it's certainly the friendliest. Okay, what about after 4? 5, okay. And we're going to test this into what equation? The second derivative. So all my buttons got changed over the weekend. Let me just check this out. Okay, so any version of the second derivative would be fine. You can use this one. You can use this one, which is actually cleaner. It doesn't really matter. You could even, if you wanted to, actually use the factored one, if that's helpful to you. So pick which version of it you'd like. Your calculator is helpful if you want to use your calculator. If you can do it in your head, that's great too. But what we want to know is we want to know what the sign is when we plug in 0, 3, and 5. So let's do 0 first. If I plug in the number 0 into any of those 3 versions of the second derivative, do I get a positive or do I get a negative? Positive. I do. I get a positive. That was fun. Try that. All right, how about when I plug in the number 3? Negative. It's negative. And what about when I plug in the number 5? It's positive. Okay, and if you didn't get those that quickly, do you at least know how we got them? Okay. So here, we don't have, like we did earlier, increasing and decreasing ideas. We have concave up and concave down ideas. So what does positive mean? It means it's concave up. Negative means it's concave down, and then a positive means it's concave up. Now, it talked about discussing inflection points and discussing concavity. So there's 2 pieces of information we're giving as answers to this question. Points of inflection and points of descriptions of concavity. Points of inflection are places where the concavity changes. What are the x values for where your concavity changes here? 2 and 4. So my points of concavity need an xy ordered pair, and right now all I have are the x values. So points of inflection, I'm going to abbreviate INF. So they're at 2 something and at 4 something. How do I find the corresponding output values for those particular x's? Plug it in the original equation. Very good. So my original equation at the very beginning up here, this is what I had before we multiplied it all out, which might be a little bit friendlier, might not, I don't know. But if I plug in the number 2, what will I get? See, I don't think my answer on my paper is right, actually. So 2 and negative 2 cubed. I think negative 16 sounds right. I don't know why that's in red. Let's try it again. And then how about when I plug in the number 4? That one's 0, yeah. So I have points of inflection at 2, negative 16, and at 4, 0. And then I have concavity issues, right? So what about the concavity? So where does the concavity, what does it do? Well, I have negative infinity to 2. And what's it doing from negative infinity to 2? It's concave up. It's opening upward. Yeah, so my concavity, let me just shift this down a little bit. This is going to be concave up, negative infinity to 2, and then where else? 4 to infinity. Yep. So that's concave up. And how about concave down? Yeah, 2 to 4. Okay. Those are all the pieces of information we were asked to find. Yes? Great. All right, so at the beginning of this section, and if you look back at the title, it talks about concavity, but it also talks about the second derivative test. And now we've used the second derivative to test for concavity here, but that's not actually the second derivative test. It's more like using the first derivative test to determine the second derivative's information. So what is the second derivative test? Well, the second derivative test actually talks about finding those potential points of inflection. And instead of making a number line, we plug those values as inflection point values back into the original equation. And if the original equation gives you a positive, then it's concave up. And if the original equation gives you a negative, it's concave down. So we're not using intervals surrounding those points like we did with that number line. We're actually using the points of inflection themselves. Okay? So that's what this says. If the second derivative evaluated at the derivative location, this is not actually written in here right. Hang on just a second. I'm sorry. I just misspoke what I said earlier. So we take our point, says, let me just read it the way it says it. Let f be a function such that the derivative is 0, and the second derivative of f exists on an open interval. If the second derivative is negative, then we have a local maximum. If the second derivative is positive, we have a local minimum. So they aren't talking necessarily, they are talking about concavity. They do tell us about concavity, but in particular, they tell us about where we have local maxes and mins. Okay? All right, that's what I misspoke on. It was the local maxes and mins part. All right, so I'm sure there's an example that follows. Let's check it out. Yep. All right. Two examples using the second derivative test. So it's actually asking us to find relative extreme points. When do I have maxes and when do I have mins based on the second derivative, which tells us information about concavity. So I need to find out what the first derivative is in order to get those places where it's equal to 0. That's what this is saying right here. And then I'm going to take those values and I'm going to plug them into the second derivative to see whether or not they're concave up and concave down at those points. So first and second derivatives. And we have what kind of a rule that we're going to have to deal with here? A quotient rule, you got it. So quotient rule, or if you want to change it into a way to do a product rule, you could do that too. But for quotient rule, what would we do here? OD high. So the denominator times the derivative of the numerator. So what's the derivative of this numerator?
2x.
Good. And then it's subtraction. And then we switch it. So the numerator, x squared plus 1. And what's the derivative of the denominator? 1. And all of this is written over x squared, right? The denominator squared. All right, so we're going to clean up what we have. I have 2x squared minus x squared minus 1 over x squared, which is what? X squared minus 1 over x squared. Okay, pretty good with that. Now I need to find out, according to the second derivative test, where this is equal to 0. And the location where it's equal to 0 are places where I potentially have max and minimum values. Okay? So all of that's just like I did back in the earlier sections, finding maxes and mins, or at least potential maxes and mins. So I need to find out where this is equal to 0, or potentially equals to does not exist, right? That's the other option. Now the reality is, the does not exist part you can probably answer really quick. When does this not exist? When x is equal to 0. But what is really happening at x is equal to 0 here? It has an asymptote, right? The original function, when x is equal to 0, it has an asymptote. I'm not getting any maxes or mins out of that. Are you with me? I can see that on this particular function. You can't always determine that on a particular function, but on this one, it's very clear. So I don't need to worry so much about the does not exist part because I know what happens there, and it's not a max or a min. But I do have places where the derivative is equal to 0. How do I find when I have a rational function where the derivative is equal to 0, or where this is equal to 0, this function is equal to 0? I need the numerator equal to 0, exactly. X squared minus 1 equals 0. You might be able to just tell me that, glancing at it right quickly. Maybe you can't. But if you can, what do you see for the or for when this numerator, x squared minus 1 equals 0? And negative 1. So there's two ways to do it. One, you could move it to the other side and take a square root. And if you do, you know to remember that when you take a square root, you do plus or minus, okay? That's one way to determine that this is x is equal to 1 or negative 1. Another way to determine it, if you don't like that option, is it's actually very much a factorable function because it's a difference of squares, right? I don't care which of those ways you do it. You get 1 and negative 1 either way. It doesn't matter, okay? So we have 1 and negative 1, and those are places where I'm going to potentially have a derivative, a local max or a local min. And the second derivative test says that the way that I can test that, like another way, like one way you know that we can set up a number line, we could do intervals, right? That's one way to do it. That's the first derivative test. The second derivative test says I could test this by taking the second derivative and evaluating it at 1 and negative 1. So that's what we're going to do. We're going to take the second derivative. So my cleaned up version of the first derivative is where I'm going to start, right there in the box of red. So I want the second derivative of that. And that one will be another quotient rule, right? So I have the denominator, x squared, times the derivative of the numerator. So what's the derivative of that numerator? 2x. And I have minus the numerator, which is x squared plus 1, times the derivative of the denominator. What's the derivative of the denominator? 2x. I'm running out of space. Let me make this just a little smaller. You guys are already cleaning up the numerator. What's my denominator going to be? X to the fourth, right? It's x squared squared. Okay, so some of you have already started cleaning up your numerator to notice that some things are canceling out. So this is 2x cubed. And then if I distribute the 2x through here and the negative through, I end up getting negative 2x cubed and negative 2x. Does that look right? So what happens to the 2x cubes? Yeah, they add to 0. So we end up with 2x cubed over x to the fourth, right? Okay, now I realize that that will reduce. Do you realize that that will reduce? I didn't mean x cubed, 2x. Sorry. And that was a gigantic eraser. Let's try this again. 2x over x to the fourth. That reduces, though. Sorry, I was jumping ahead of myself. What does it reduce to? Yes, negative 2 over x cubed. Yeah, and there's negative. I keep losing my negative. I'm so sorry. That negative is really important for what we're doing, too. Really important. All right. So we have negative 2 over x cubed. All right. We're not setting up any sign charts. We're not setting this equal to 0. That's not what the second derivative test says. The second derivative test says I can take this second derivative, that's my notation for it right there, right? And I can evaluate it at the locations where the first derivative is equal to 0. 1 and negative 1. And again, I'm looking at signs. Do I get a positive or do I get a negative when I do this? So when I plug in the number 1 here, do I get a positive or a negative? I get a negative on this one. And when I plug in the number negative 1, do I get a positive or a negative? Yep, I get a positive. Okay, so negative means that it's concave down, and positive means that it's concave up. So those pieces are just like they were before. But we never did a sign chart, right? We didn't. We didn't do a sign chart to do it. We did it using the second derivative to determine, and again, the second derivative determines concavity, concave up, concave down. But that's not what the question asked about, right? It asked about maxes and mins. So imagine if you have something that's concave down, looks something like that. Do you have a max or a min? You have a max, yeah. Right here, this would be a max. And if it's concave up, do you have a max or a min? You have a minimum. Okay, right? So this point right here, which corresponded to x equal 1, is a location of a relative maximum or a local maximum. And this place where I had -1 is a local minimum. So my screen's getting too small very quickly. Let me see if I can shrink a whole bunch of stuff and shift it a little bit. So I'm trying to decide about the relative maxes and mins. And remember when I wrote these out earlier, it's been a few days, I know. What I did is I said things like this. There's a maximum of something at x equal to a value, and there's a minimum of something at x equal to a value, right? This is how I structured my language. So let's go back and figure out what I have. Right now, I know that I have a maximum at x equal 1. So this is 1 here. And I have a minimum at x equal to -1. But how do I determine what the maximum and minimum values actually are? The original function tells me that, exactly. So let's go back and take a look. If I were to plug x equal to 1 into the original function here, what am I going to get? I'm going to get 2. And if I plug in x equal to -1, what am I going to get? I'm going to get -2. Where'd my screen go? Oh, there it is. I'd like to make a mention of something very interesting right now. You might look at that and go, okay, well, maximum 2, minimum -2. Well, of course, that -2 must be the minimum. Then why did I even need to figure out the rest of it? Why couldn't I have just taken x equal to 1, x equal to -1, and skipped the whole second derivative test? Because it kind of looks that way, right? I mean, -2 is smaller than +2, so obviously it's the minimum and the other one's the maximum. The reality is it doesn't always work that way, and I want to draw you a picture to show you why or how it could fail to have that happen. Especially with rational functions. So let's say, for instance, you had a function that looked like this. Do you want it to look like that? Not quite. Okay. Yeah, that'll work. Okay, so this is a made-up image, and I get that. But there are functions that would create images somewhat similar to this. What I want you to recognize is, that's what's wrong. I was like, part of my picture's not quite right. We'll go with this. That's better anyway. Is that right now, if you're taking a look at it, this one right here is a minimum, correct? Because in the local area, right, if I were to draw a circle around it, it's the smallest value. It's a minimum. And this one right here is a maximum. Agreed? But do you notice that the minimum y value is actually larger than the maximum y value? So that can happen. I mean, just really can. And it's particularly happen a lot of times when you have rational functions. Polynomials don't have that kind of feature going on. It doesn't work quite like that. But rational functions can have some really weird things happening. So just be aware of the fact that it's not always true that a local maximum is actually bigger than a local minimum. All right, another question. Signs, because we got to do some trig. No? Yes, we do. Absolutely we do. One of my daughters actually asked me this morning, Mommy, what is trig? And I said, it's math. Yeah, that's what I told her. She was like, oh, okay, that was good enough for her. Yeah, started early, I know. All right, so let's take a look. We are going to do the exact same process we just did on the last question, which means we need a first derivative, we need a second derivative. So what is the first derivative for sine of x over 2? Okay, so the derivative of the sine is the cosine, and the inside stays the same. And then, Jeff, you're already jumping ahead of telling me that the derivative of x over 2 is 1/2. Okay? And it is. It's not a quotient. I know it looks kind of like it's a quotient. It's really just, x over 2 is really just 1/2 x. Right? And the derivative of 1/2 x would be 1/2. So if you're comfortable going ahead and putting it, you can put the 1/2 at the beginning. That works just fine. Okay, so then, notice my interval on which I'm looking is actually 2 periods, from 0 to 4 pi this time instead. That's okay, we can do that. Now what we actually, and there's a reason for it, I'll mention it in a minute, but what we actually want to do then is we want to consider where this derivative that I just found is equal to 0, right? So where in the world do I get cosine values specifically that are equal to 0? Just think about cosine itself. At where? Pi over 2. Yeah, the 90-degree angles, right? So like at the top of the unit circle and at the bottom of the unit circle. Is everybody good with that imagery? Fabulous. So pi over 2 and 3 pi over 2. And I actually want to go the full rotation twice for the moment. I'll show you because you might need more. It's not always easy to tell. So it would actually be at all the pi over 2's that are odd, right? So 5 pi over 2, 7 pi over 2, and it could keep going if we needed it to. Everybody good with that? Okay. But what we want is we want that this angle is going to be equal to those particular angles, correct? So we actually want our x over 2 to equal these potential angles. Agreed? Our angle happens to be x over 2. The 1/2 at the beginning, does it matter for the purpose of where this thing's equal to 0? Nope, it doesn't change anything. If the cosine part's 0, the 1/2 gets zeroed out when we multiply. Okay, cool. So, but the fact is that I want to solve for x. So what am I going to do next? Multiply everything by 2. Now, this hopefully, especially if you've taken trig here at OBU, this should look familiar because I know we do this in our trig class here where we solve equations set equal to 0 and things like that. Double angles and half angles. So this would be a half angle because x over 2 is half of an angle. So I end up with x on the left, and what happens to all of the denominators on the right? They cancel out. So I actually end up with all of the odd values of pi, odd multiples of pi. So pi, 3 pi, and I would keep going, right? 5 pi, 7 pi, it would keep going for reals, except that I don't care about all of them. I only care about going up to 4 pi. So the only ones that actually fit the description for the interval I'm looking at are pi and 3 pi. Okay? Doesn't always happen. I could actually end up having to keep going further. If this had been a double angle, like instead of it saying pi over 2, it said 4 pi or something like that, and I divided, I could have to keep adding more values. Like that's a possibility, depending on what I'm working with. So I only have 2 of them, pi and 3 pi. But I don't know if either one of them is a max or a min, and so I'm going to do a second derivative to determine that. So I need to find, the second derivative of my function. So what is the derivative of 1/2 cosine x over 2?
-1/4 sine x over 2.
Okay, so cosine becomes negative sine. So that's the negative. And then the derivative of the x over 2 is another 1/2, which makes it 1/4. And the angle stays the same on the inside. So everybody see where all those pieces came from? Because we're cleaning things up kind of as we're moving along since I don't have a lot cleanup to do. And I'm using then the second derivative to evaluate the points that I've got. So that's the pi, so the second derivative at pi, and the second derivative at 3 pi. Okie dokie, so if I plug in negative 1/4 sine, and this is now pi over 2, what's the sine of pi over 2? That's at pi over 4. We have pi over 2. It's 1. Yeah, the sine of pi over 2 is at 1. So this ends up being negative 1/4, or in particular, what I care about, of course, is the fact that it's negative, right? Yeah, and then I've got 3 pi over 2. So I have negative 1/4, and I have sine of 3 pi over 2. So 3 pi over 2, sine of 3 pi over 2 is negative 1. With the negative 1/4 already in there, it becomes a positive 1/4. In particular, again, I care about the fact that it's positive. Okay? And you could evaluate those in your calculator just fine if you're not super comfortable or remembering details of your unit circle right now, right? Yeah, you can do that. All right, so what does the negative and the positive mean? Well, negative on a second derivative means it's concave down, right? And positive means it's concave up. And then the second derivative test that we saw before also told us that a negative here, or we can draw a picture if we're feeling uncomfortable at it, concave down, means that I have a max. And a positive means that I have a min. So it looks like this visually, right? Okay, so we're going to interpret this now. I have a maximum of something at x equals to pi. And I have a minimum of something, we'll figure out what it is again here, at x equal to 3 pi. Okay, those are my max and my min statements. I just need to figure out what happens at pi and at 3 pi. So going back to the original function, sine of x over 2, what is the value when I plug pi into that? It's into the original function. Like, what is the sine?
1.
Yeah, it's 1. So if I go back and I take f of pi, I would have sine of of pi over 2. And you're exactly right, that's 1, right? We encountered that one before, so this is a maximum of 1. And when I put in the negative, or not the negative, but the 3 pi, I get -1, right? Yeah, so that's a minimum of -1 at x equals 3 pi. Any questions on that? If WebAssign were to ask you to write it as an ordered pair, could you write the max min as an ordered pair using that information? Sure, you could. Sometimes resources will ask you to do that. I don't remember which way WebAssign actually asks you to do it, but you could certainly write that as an ordered pair if you needed to.